Okay, let's keep talking about the dot product. Last time we came up with this nice geometric interpretation of what's happening with the dot product, but it was very precise, right? We found out that the dot product is actually can be computed in this other way by multiplying the lengths of the vectors and then multiplying by the cosine of the angle between them. And remember, we use this picture and the law of cosines to sort out why that was true. Now, don't forget that, you also have that u dotted with v is just, u1 v1 plus u2 v2 plus u3 v3. And so you just multiply the respective coordinates together and add together the results. And before we even had this formula, we suspected that the dot product was telling us, like if it was positive, that the vectors were tending to help each other. And if the dot product is negative, that the vectors were tending to oppose one another, yes, or hurt one another. And this formula right here, 100% verified that fact, okay? So again, another way to write this, well, first of all, we also realize that if the vectors are at 90 degrees to one another, then the dot product is 0, yeah? Because the cosine of 90 degrees is 0, right? But another way that the dot product could be 0 is if one of the vectors is 0, so we had to invent a whole other term to encapsulate the fact that the dot product is 0. It's not just that the vectors are perpendicular. That's one way that the dot product could be 0, but also one of the vectors could be the 0 vector. But if two vectors are non-zero, then their dot product being 0 means that they are perpendicular to one another, yeah? But the term we invented is this, this funny thing, orthogonal, yeah? Orthogonal, okay? So here's kind of a summary of what we have. So first of all, I just want to reiterate that you can still compute this thing by just multiplying the respective coordinates together and adding the results of those products. Okay, but again, the geometric way of computing this would be this formula right here. And so cosine of the angle between them determines the SIGN, the sign of the dot product, and hence whether the vectors are tending to help or hurt one another. Okay, u and v are orthogonal when u dot v is 0. Thus, if both vectors are non-zero, they meet at a right angle if and only if their dot product is 0. Okay, so dot product 0 tells us something about vectors being perpendicular in the case where both vectors are non-zero vectors. Okay, any questions on this before we start using some of this stuff? Okay. Well, let's keep going. I want to talk about direction cosines. Okay. So like we can somewhat locate a vector in three-dimensional space. This picture, I mean, I just want to make sure this picture makes sense. Kind of in the first octet right here, the positive x-axis is coming out at us. Y-axis is kind of parallel to the screen, and the z-axis going straight up. I have I, J, and K there, okay? And essentially, I have labeled the angles between the positive x-axis and V, the positive y-axis and V, and the positive z-axis and V, which, by the way, are also the angles between those vectors I and V, J and V, and K and V, right? I've labeled those vectors as alpha, beta, and gamma, right? So we're using some nice little French, or not French, Greek letters. That'd be interesting if we used French letters, right? Because those would just be our letters. These are Greek letters, alpha, beta, and gamma, okay? Those are called the direction angles for the vector. Basically tell us where the vector lies in three-dimensional space. It's the angle off the positive x-axis, y and z-axis respectively. And it's the same as the angles between the IJK vectors as well, okay? So those angles are called the direction angles of the vector v. Of course, it's the same as the angles between v and ij and k. And if I take the cosine of those angles, those are called the direction cosines. Why would that come up? Well, it has to do with dot products. You're saying to yourself, why in the world would you specify cosines for those angles? Again, it's because of dot products, okay? Because you actually know that cosine of alpha, for instance, is equal to what? Well, I can kind of concentrate on these two vectors right here, like I and V, okay? And alpha is the angle between those two vectors, yes? So what I can do is I can say, look, cosine of alpha is equal to I dotted with V over the length of I times the length of V, right? But what is I dotted with V, for crying out loud? What is that going to do? Think about it. Remember, I is like 1, 0, 0, correct? If I dot that with the vector V, right, and remember V is just V1, V2, V3, okay, what am I going to get? Just the first coordinate, yeah? Because the zeros are going to kill the second and third coordinates. And I'll just get V1 over, now here's the thing, what is the length of I? What's the length of I? 1, yeah? So this part right here just kind of disappears and we're just left with V1 over the length of the vector, yeah? So cosine of alpha is equal to V1 over the length of V. What do you think is going to be true about cosine of beta? Well, I could do the same thing with J and V, yes? And I could do the same thing with K and V for cosine of gamma. Okay, so cosine of beta and cosine of gamma. Cosine of beta is going to be not V1 over the length of V, but V2 over the length of V. And of course, cosine of gamma is going to be V3 over the length of V. Okay? So that's interesting. So cosine alpha, cosine beta, cosine gamma, where alpha, beta, and gamma are the direction angles for the vector. So the cosines of those, which are the direction cosines, is just given by the respective coordinates over the length of the vector. Yeah? So that's interesting. That formula is going to be on this next page as well. Okay, so cosine of alpha is equal to V1 over the length of V. Cosine of beta is equal to V2 over the length of V. Cosine of gamma is equal to V3 over the length of V. That's interesting, right? So that's a nice little fact, okay, that we can take to the bank. But also, don't you realize that, do you remember like dividing by the length of a vector before to find a unit vector? Yes? Yeah? Okay. So think about it. If I take V and I divide by the length of V, then I'm going to get V1 over length of V, V2 over the length of V, V3 over the length of V for that vector. Yes? That's what the new vector is going to be. And hey, don't you see V1 over the length of V, that's cosine of alpha, yes? V2 over the length of V, that's cosine of beta. V3 over the length of V, that's cosine of gamma, yeah? So in other words, cosine alpha, cosine beta, cosine gamma, those are just the coordinates of a unit vector in the direction of V, yeah? Therefore, what happens if I sum up the squares of the direction cosines? Since those are the coordinates of a unit vector, if I sum up the squares, that's like computing the length of that vector, right? I would have to take the square root, but that doesn't really end up mattering here because the length is going to be 1, yeah? So the sum of the squares of the direction cosines ends up being 1. Okay, the sum of the squares of the direction cosines end up being 1. Okay? So let's do an example here. What if V was equal to 2, 1, 3? Okay? then what is the length of V? What's the length of this thing? Square root of 2 squared plus 1 squared plus 3 squared, which is square root of 14, yeah. So in other words, a unit vector in the direction of V is going to be V over the length of V, which is 2 over the square root of 14, comma, 1 over the square root of 14, comma, 3 over the square root of 14. But we just found out that that's really just the direction cosines as well, right? The first coordinate, V1 over the length of V, that's just the cosine of alpha, right? So that's cosine of alpha, cosine of beta, cosine of gamma, okay? So in other words, what I'm saying is cosine of alpha here is just 2 over the square root of 14. Do you see what I'm saying? So what would the angle be that this vector makes with the positive x-axis? How could I figure out what the actual direction angle is with respect to the positive x-axis? What would I use to sort out what that angle alpha is? Arc cosine, right? Alpha equals arc cosine of 2 over the square root of 14. I could actually solve for alpha, for instance. By the way, I could do the same thing for beta and gamma by using the second and third coordinates of this unit vector, okay? So surprisingly, finding a unit vector in three-dimensional space has this nice connection to the direction cosines, like what's the angle that's made with the positive x, y, and z axes, respectively. By the way, the same sort of thing happens in two-dimensional space also, okay? Any questions on that? Questions? All right, so this guy is interesting. Formula for the direction cosines, but so is this guy right here. This is a pretty interesting fact right here. It just comes from the fact that we have a unit vector. Okay. Moving on. Let's talk about vector projections, okay, and how we could get a handle on that. Okay. So in physics, we sometimes want to know how much of a vector is actually going in a certain direction. It's like how much of this force that's being applied is actually in the horizontal direction, and how much of this force is in the vertical direction, for instance. So if I'm pulling my kids in like a wagon or something, yeah, I'm going to be pulling up at an angle, at an angle away from the earth, away from the surface of the earth. Well, some part of the force I'm exerting on that wagon is going to be horizontal with respect to the surface of the earth. And some of that force is going to be vertical with respect to the surface of the earth, yes? So it stands to reason that it might be useful to know what those horizontal and vertical forces are with respect to that vector. And in general, I might want to break down a vector into a couple of different forces in certain directions. So in general, I might want to know how much of a vector is actually going in the direction of some other vector, yeah? And so that's what we're going to look at right now, is if I have a vector and I think of it as a force and I have some other vector, I want to know how much of the first vector is really kind of acting in the direction of the other vector, okay? And here's like a typical problem you might have. Okay, a 10-pound bowling ball is on a ramp inclined at 45 degrees. Okay, so here's a ramp. You just draw this thing. And this thing is supposedly inclined at 45 degrees, which is pi over 4, yeah? So here's my bowling ball right here, okay? And this thing weighs 10 pounds, okay? The only reason it's not rolling down is the force that you're applying with your hand in the direction parallel to the ramp, okay? So like this bowling ball is wanting to go down at some kind of force, and my hand is right here, okay? Here's my hand. right? I don't know, it looks like a claw or something like that, right? And my hand, it has to exert some kind of force in this direction to kind of keep the ball in place. Yes? This thing weighs 10 pounds, but of course those 10 pounds are coming from gravity. Yes? There isn't necessarily going to be 10 pounds of force going down that ramp. The 10 pounds is in a perpendicular direction with respect to the surface of the earth, yes? And the question is, how much force am I having to exert on this ball in order to keep it in place? Does that make sense? Of course, I'm neglecting things like friction and things like that, right? But the question is, how much force am I having to exert on this thing to make sure it doesn't go rolling down that ramp? Okay? In all likelihood, it's, what do you think, less or more than 10 pounds or the same as 10 pounds? What do you think? Probably less, yeah? I mean, think about it. If this ramp was almost like horizontal, like if it was barely an incline at all, I would almost have to put no force at all on that ball to keep it where it is, yes? Okay. So in this case, I mean, I'm going to have to exert some force, but it's not going to be 10 pounds of force. It's going to be less than that. And we're going to figure out how to sort out problems like this, okay? All right, so let's have a look at projection in general, okay? How much of a vector u is going in the direction of v, okay? So let me just draw a little picture here. Here's u. And I don't know, here's v like this. Here's the vector v. I'm going to use red just so it stands out a little bit better. Okay, so there's v, and here's u. And the question we're asking is, how much of the vector u is actually going in the direction of v? So like there's a part of this vector, if I kind of imagine this thing casting a shadow in a perpendicular direction on v, there's a part of this vector that is actually moving in the direction of v. Does that make sense? Okay. And so what you do is you kind of break down this vector into two components. You call this one W1, okay, the one that projects down onto V. And then you call this other thing W2. And of course, U is equal to W1 plus W2. And W1 is parallel to V, right? It's kind of the shadow of U on V. It's the projection of U onto V. Okay, so that's kind of the picture that I have in mind. Now, here's the thing, W2, once you have W1, okay, once you have W1, W2 is pretty easy to find. You just have to take the difference, right? So W2, of course, is just U minus W1, okay? Right, so this guy, W2, is just U minus W1. We've thought about that geometrically before, okay? But of course, the equation works out nicely that we've written down here anyways. U is equal to the sum of W1 and W2, therefore, W2 is the difference between U and W1, yeah? Okay. So we're gonna think about how to come up with a formula for W1. That's the key. Once you know W1, W2 is easy, okay? How do I get a handle on what the projection of U onto V is? So we'll kind of sort that out now. And somehow the dot product is going to be involved. Okay, so this is just a repetition of what of the setup we just had, right? So W1 is parallel to V. Here's a better picture than the one I drew before. Okay, V's down there, U has projected onto this. Of course, the picture I drew, the angle theta between the vectors was acute, yeah? Of course, it doesn't have to be, it could be obtuse. It could be greater than 90 degrees, okay? And by the way, W1 gets a special notation. I don't know if you can see that little V down there, but basically what we're writing here is W1 is the PROJ, which is the projection of U onto V. Okay, V goes down there because you're almost thinking of V is receiving the projection down from U, yeah? Okay, so W1 is called the projection of U onto V. Now, what do you think is going to help us sort matters out here? Well, it's got to be, right? That's a right triangle, isn't it? Do you see that right triangle? Yeah. And if I want to figure out, like if I just kind of stare at this right triangle right here, so W1, right? V only goes to right there, and W1, if I project down, it's actually longer than V in this case, the way that I've drawn it, yeah? But what about the length of W1? What about the length of W1? Do you see a trig function that might actually help us sort this thing out? Okay, look, I have this angle theta right here in this triangle, yes? Okay. U is the hypotenuse of the triangle, correct? The thing I'm talking about right now, W1, that is the adjacent side of that triangle. So what trig function would help us here? The cosine would, yes? The cosine actually would. So like length of W, that's adjacent over the length of U. That is equal to cosine of theta. Okay? So in other words, the length of W1 is equal to the length of U cosine of theta. Okay? The length of W1 is equal to the length of U cosine of theta. Okay? So, how could I come up with a formula for W1 then? Think about it. How could I come up with a formula for W1? Couldn't I go like this? I mean, just think about this. W1 is equal to, look, I want a vector that's basically parallel to V, correct? But what do I want its length to be? Didn't I just come up with that? I want its length to be given by that, yeah? All right. So look, it's going to be V, but then it's like, I'm going to kind of shrink it or, stretch it to a length 1 at first. How would I shrink or stretch this thing to a length 1? What do I do to V? Because what I'm going to do is I want to actually make this have the length that I want, namely this, this length right here. But at first, I just know that it's the length of V, whatever it is. To make it length 1, what do I do? Yeah, so I'd go 1 over the length of V. Okay. So at that point, this guy is like length 1. So this is length 1. But that's not what I want. I want to actually have something that's of length W1. So I want to multiply this by the length of W1. Okay. So what do we end up with here? Well, it's going to be the length of V times, what's W1 again? Didn't we just figure out what W1 was? Yeah? What was it? Length of U cosine of theta, yes? So it's going to be length of V times length of U. Oops, let me write this in red just so we can see it better. Length of U cosine of theta over length of V. Okay, so that's what the projection formula is. That looks horrible because it's like length of V times that thing right there. All I did was I said, okay, I want the thing to have the proper length. So I made it length 1, and then I stretched it back out to the length that I want by multiplying by length of U cosine of theta. But here's the thing. Length of U cosine of theta is almost like, length of U cosine of theta, that's almost like the dot product, remember? Well, the dot product is like length of U, length of V cosine of theta, yes? So here's the thing. I can actually tweak this a little bit more and have V times length of u times the length of v times cosine of theta. But I can't just like a maniac multiply the top by length of v but without also doing what? Multiply the bottom by length of v. So what's going to be on the bottom now? Length of v squared, yeah. And now what's upstairs? Okay, so I have length of v, since I'm projecting onto v, and I'm taking a scalar multiple of the length of v. What is that scalar? Well, upstairs, that's length of u, length of v, cosine of theta. That's just the dot product. So it's actually u dotted with v divided by the length of v squared. I mean, I could write that length of v squared. Look, I could write that in a different way. What is that? V dotted with v. And there's the formula for the projection. There is the formula for the projection. It's right there. Okay, that's pretty interesting stuff, right? So W1, which is the projection of u onto v, you just take u dotted with v over v dotted with v and take that scalar multiple of v, and that will give you the projection. All of it just comes straight out of trigonometry. We're just doing some trigonometry using the cosine function. Okay? So that's what's going to be on the next slide here. We have this formula right here. Of course, in this version of the formula, I just left length of v in there. But of course, that guy right there could also be written as v dotted with v, correct? Yeah. Okay, so the projection of u onto v, what do? I take u dotted with v upstairs, and I take v dotted with v downstairs, and I take that scalar multiple of the vector v, yeah? Since I'm projecting onto v, it's got to be some scalar multiple of v, and we just sorted out what that is. That's how I get the projection, right? So in our picture over here, this projection is just W1, okay? So that's what W1 is, projection of u onto v. That way, we can always determine, if I have two vectors, I can always determine how much force from the one vector is exerted in the direction of the other. Okay. Any questions on that? It's kind of an important little formula about vector projections, but any questions on that? Okay. Moving on. Back to our problem about the 10-pound bowling ball. Yeah? Okay, so here was this. Okay, let's just imagine, okay, this ball is sitting here. Let's just imagine that this vector right here represents the bowling ball's force all the way down, okay? Okay, so this is the bowling ball's force along this guy right here, okay? Then I'm gonna have to figure out, so first of all, you know something about this thing. So this is pi over 4. Okay, this ball exerts a force in a direct downward direction. What is that? What's the force in the direct downward direction? What's that, Daniel? Yeah, that's 10 pounds. Okay. Okay. So, what we need to do is figure out, look, what is the project? So I don't know, let's call this vector right here G for gravity, okay? Okay, so what are the coordinates of that? Look, if I think of the coordinates as being kind of like pounds or something like that, yeah? Okay. What are the coordinates of this vector? 0, then what? -10. Okay. Don't I want to know? So like here, let's call this thing, this bowling ball is kind of going down this ramp like this. Let's call this vector, I don't know, B for the bowling ball itself. Yes. Okay. Okay. So here's the thing. Look, one thing I want to make sure that we're clear on, if I take the projection of U onto V, okay, you know that this is going to be U dotted with V over V dotted with V. Okay, that scalar times V, yeah? What happens if I compute the projection, the length of the projection of U onto V? What's going to happen if I compute the length of that projection? Now bear in mind that U dotted with V, you guys realize that that's just the length of U, the length of V times the length of V times cosine of the angle between, yes? Okay. And what about V dotted with V? That's just the length of V times the length of V, yes? It's just the length of V squared. So what's actually going to cancel here? What actually cancels, we created this so that it was an easier formula to remember. But what actually cancels in this, we have to keep that in mind. What's going to cancel? The length of V would cancel, yes? And then if I compute the length of this projection, basically what I have left is V over the length of V, yes? What's the length of V over the length of V? 1, yeah? So that part would kind of go away if I was computing length. These length of V's also cancel, and the projection itself has length. We already computed this before. Has length, the length of U times cosine of the angle between. Yeah? Okay. So if I were to project, think about it for a second. If I were to project this gravity vector onto this thing over here, and by the way, this gravity vector, I don't know, it's so that gravity vector is, I have 10 going in this downward direction. What would happen here if I were to kind of break down? So, I mean, what I'm saying is, what would I have to do to actually figure out how much force this thing that I'm going to have to exert with my hand in this direction? By the way, this picture is probably a little bit misleading because this vector right here looks like it's kind of long, but really I need to figure out this guy right here is going to project, this gravity vector is going to project something over here, and that's going to really determine what the force is, yes? Okay? Right, the force that we're going to have to exert is given by the projection of this thing over here. So what were you going to say, Daniel? Okay. Oops, I just... Say again? So could you find the value of vector B and just find the negative and that's the force? Right, well, but B, I'm saying that's just like the whole vector on that whole side. But the force itself is just this this green thing that I drew right here. Does that make sense? Okay, so I have to think about this gravity vector sort of projecting right here. So B is this entire thing right here, yeah? But then I have to figure out what this other force is right here. I don't know. So here's this force that's being exerted by the bowling ball. Yes. Okay. So what is the projection? Well, okay. So like, what is the length of the projection of G onto B? Isn't it just going to be the length of G times what? Cosine of the angle between these things, right? And so this vector right here is also pi over 4, okay? So it's going to be the length of G, which is 10, times cosine of pi over 4. And what is the cosine of pi over 4? square root of 2 over 2, right? So what would we end up with? 5 square root of 2. So let me ask you a question. So that right there, okay, right, the length of this projection, by the way, is also the length of this force vector, yeah? 5 square root of 2. Is 5 square root of 2 smaller than 10? Yeah. The square root of 2 is like 1.414 or something like that, correct? So how much force am I going to have to exert to kind of keep that bowling ball in place up here? 5 square root of 2 pounds, yes? Since I'm pushing parallel to the, in the direction parallel to the ramp. So this right here is the pounds of force. Pounds of force. Pounds of force necessary. Okay, so you had to figure out what the, what the gravity vector actually projected onto that side over there. Yeah. I forgot to put the other side of this vector thing in there. Yeah. All right, any questions on that? Okay, little bowling ball rolling problem, okay, that involves vector projections. Don't forget the formula for the projection of one vector on another, but also don't forget the formula for the length of the projection. That's pretty easy thing to remember also, okay? Another way to write this, by the way, would be length of u, length times the length of v times cosine of the angle over the length of v, which, by the way, is u dotted with v. Okay, really, I should take absolute values of this over the length of v. Okay, I should take absolute values of that because the dot product could potentially be negative. But the length of the projection formula is also kind of a nice one to have in mind. Okay. Did I ever have to find the coordinates for the vector f to solve this problem? No, I didn't. All I had to do was figure out what the length of that force vector was. Okay. Any questions on that? Let's talk about work, okay, as a physical quantity. Do you know how to calculate work done by a constant force along the line of an object moving it a particular direction? Does anybody know? Force times distance. Yeah? So it's basically, whatever that force is times the distance that thing has to move. But that force is assumed to be in the direction that the object is moving. But here's the question I have. If I exert a particular force in my wagon pulling problem, so suppose I exert 20 pounds of force in kind of like an upward diagonal motion as I pull my wagon, the wagon is moving horizontally, yes? So is all of my force that I'm exerting in this diagonal direction actually in the direction of the moving wagon? No, only a part of it is. And to figure out what portion of that force is actually moving the wagon along, I would have to use vector projection. Yeah? So let's talk about that. Again, if the force is parallel to the direction of the movement, so here the force is literally parallel to this thing, then the force is just going to be, or the work is just going to be force times distance, and the force is just given by the length of that force vector, yeah? And you would multiply that by the distance the object is moved. Okay, this is how we measure the amount of work done. How much force, how much distance is covered in moving that object with that force, okay? So what do we do if the thing is not, the force exerted is not parallel to the movement that happens, kind of like my wagon problem, yes? Well, what we would have to do is actually take our force vector F. So here's me kind of pulling in an upward diagonal motion with my wagon, yes? And I would actually have to project this thing down to the direction parallel to that of movement, yeah? So that would just be the projection vector that we've been working with, yeah? Okay, so what would be the formula for work? Well, it would be the length of that projection vector because that is the true force in the direction of movement, yeah? It would be the length of that projection vector times the distance vector, okay, PQ. Okay, you can even form a distance vector here, where P is the place where the thing started, Q is the place where the thing ended, okay? Well, that's interesting, but we actually have a formula for the length of the projection, right? We just computed that on the last slide. What is the formula for the length of the projection? It simplifies to simply the length of F times cosine of the angle between them, yes? And lo and behold, now I have length of F, length of PQ, times the cosine of the angle between them, and lo and behold, that is just the dot product, yeah? Length of the one, length of the other, cosine of the angle between them. And there it is. So the true formula for force is not just one number times another number. It's really like a force vector, whatever the force is, whatever direction that force is being exerted. It's that force as a vector dotted with like the distance vector, PQ. So PQ is the vector that represents where the object actually moves. Does that kind of make sense? Now, again, this force has to be constant throughout. There's lots of questions that ought to be swimming around in your mind right now. Like, for instance, what if I get tired as I'm pulling my kids along? Is that, you know what I'm saying? And suddenly I'm not exerting 20 pounds of force anymore. I'm only exerting 12. And then suddenly I see Chick-fil-A up ahead and I get a new zeal for pulling and I increase my pulling strength to 30 all of a sudden. So over time, my force actually varies. It gets higher and then lower, etc. This formula for work, unfortunately, requires a constant force. And it turns out that the question I just asked, what do we do if we have variable force at different points in time? That is a question that we need a lot more machinery to handle. It's going to require an entire other course, actually, to handle, okay? Variable force at different points in time we're going to have something called a line integral in three-dimensional space that will actually help us deal with that situation, okay? And actually that situation where I have variable force at variable time is much more reflective of reality, yeah? You're not just gonna have a perfectly constant force the entire time. So that's something that you'll look at in Calc 3. Be exciting. Okay. Well, let's look at an example of this. So again, if you really want a true formula for work, it's going to be the force vector that's exerted dotted with the distance vector. And by the way, the work could be negative. Okay, here we're kind of measuring the amount of work that's being done by this force field in collaboration with the distance vector. You could literally have a force that's working against it, like wind, for instance. Does that make sense? Yeah. So you could have like a wind force that's actually working against this, in which case the dot product would actually be negative. Okay. So that's something to keep in mind. Next. Work W done by a constant force F as its point of application moves along the vector PQ is one of the following, right? You can either just, compute it with the lengths of the projection and PQ, or you can just straight do the dot product form of the thing. It's basically a summary of what we had on the last slide. Okay. So here's an example that we'll close with. To close a sliding door, a person pulls a rope. Okay, so here they are right here, pulling this rope. See this force vector right here? Yeah. Person pulls a rope with a constant force of 50 pounds at a constant angle of 60 degrees. Okay, as shown in figure 11.34. Find the work done in closing the door 12 feet to its closed position. Okay. Well, okay, so what's the length of PQ? What's the length of PQ in this case? 12 feet. Okay, what is the length? So we have this force vector right here. The projection vector is up here somewhere, right? It's the projection of F on PQ. The length of F, or the length of, sorry, let me write this correctly. The length of the projection of F onto PQ, which is what we really need, that's going to be the length of F times the cosine of the angle between F and PQ. Yes? But what is theta in this case? What's that? Yeah, 60 degrees. So this is going to be cosine of pi over 3, which we know, hopefully. Okay. What is the length of F? 50 pounds. That's interesting because this 12 right here was in feet. Yes? And I'm about to express the length of F in pounds. But is that okay? Yes, those are units of force. Force is foot pounds. Yes? Okay, so this is going to be 50 times this. Okay, so what do I get here? 50 times, what is 50? What's cosine of pi over 3, basically? It's a half. Okay, so this guy right here is 1/2. Okay, and I get 25. Okay, so what is the work? Well, it's going to be the length of the projection of F onto PQ times the length of PQ, which is 50, or no, not 50. What is it? It's not 50. It's how many pounds? 25 pounds times 12 feet, which is what? What's that? 300 what? What are the units? Foot pounds. 300 foot pounds. Exactly right. Okay. All right. We're done with dot products.